viewers, in my lecture on biomolecules, in my last lecture, we had discussed the open chain structure of glucose, and we saw many of the properties of D-glucose can be explained in terms of open chain structure. That is, glucose has one aldehyde group and 5 hydroxyl groups. And it clearly showed that it has an aldehyde group because it reacts with bromine water to form gluconic acid. That is, it decolorizes bromine water. It also reacts with Fehling solution, Benedict solution and Tollens reagent, thereby indicating that it has an aldehyde group. It undergoes reduction with sodium amalgam to form glucanol. In this case, the aldehyde group is reduced to an hydroxyl group. It also reacts with acetic anhydride in presence of pyridine to give us a pentaacetate. And the 5 acetate groups are attached to 5 different carbons. That means it has 5 hydroxyl groups, and all the 5 hydroxyl groups are attached to different carbon atoms. We have also seen that glucose on reduction with HI and red phosphorus formed an hexane, which indicated that the 6 carbon atoms are present in straight chain in glucose molecule. But what we found that some of the reactions were not explained by open chain structure. That is, it could not explain the fact that despite having an aldehyde group, glucose does not undergo reactions with sodium bisulfite to form an addition product. It does not react with ammonia also. D-glucose gives a negative test with Schiff's reagent. And we know Schiff's reagent is a special reagent that requires a relatively high concentration of a free aldehyde group in order to give a positive test. And also this molecule does not give positive 2,4-DNP test. So what happens in 2,4-DNP test? That is 2,4-DNP is 2,4-dinitrophenylhydrazine, and when glucose is treated with this, it does not give us a yellow, orange or a red color, which is the characteristic reactions of aldehyde groups. So that means from this we can conclude that the aldehyde group is either present in very small amount, as it is giving the other test which I have discussed, or it is present in a cyclic form, or it is not free to form give these reactions. Second, what was found that when glucose is treated with hydroxylamine, and this we saw in our last lecture also, it forms an oxime. But if glucose is converted to pentaacetate by reaction with acetic anhydride in presence of pyridine, this does not react with hydroxylamine. That is, the pentaacetate does not react with hydroxylamine. This clearly shows that the aldehyde group is not present in glucose pentaacetate. So that means where is this aldehyde group now? Why is it glucose not giving the reactions of aldehyde, some reactions of aldehyde groups? And then what was found that the open chain structure could not explain the phenomena of mutarotation. What is mutarotation? Mutarotation is change in specific rotation of aqueous solution of glucose when allowed to stand for some time. You know what is specific rotation? Specific rotation is rotation of an optically active compound that it has a tendency to change the path of plane polarized light, and this specific rotation stays constant over time. It does not change with time. But what was found that when glucose was dissolved in water, its specific rotation changed with time. So what was so peculiar about glucose that its optical rotation was changing? And this could not be explained on the basis of open chain structure. And you also know that if a molecule has an aldehyde group, it reacts with alcohol to form a hemiacetal, and it reacts with excess of alcohol in presence of HCl to form acetal. Now, what is hemiacetal? Hemiacetal is a molecule in which a methoxy group, a alkoxy group, and a hydroxyl group are attached to same carbon. So hemiacetal is formed when aldehyde is treated with one molecule of methanol. We get this hemiacetal in which carbon is attached to a methoxy group as well as to a hydroxyl group. And when this reaction is carried out with excess of methanol in HCl, we find an acetal is formed. That is, two methoxy groups are attached to the same carbon. But this was not the case with glucose. When glucose was treated with methanol, in presence of HCl, what was found? Two isomeric methyl glucosides were formed, which were alpha D and beta D methyl glucosides. The open chain structure cannot explain this, because in case it was an open chain structure, the reaction with methanol in presence of dry HCl would have resulted in formation of an acetal. That is, the two methoxy group would have been attached to the same carbon. But in this case, what is happening? We are getting two isomeric methyl glucosides. That one of the carbon atom is asymmetric. That is, it is a stereogenic center. That only we can explain the formation of two methyl glucosides. And what was further found? That these two glucosides did not reduce Fehling solution, and they also did not react with HCN or hydroxylamine, indicating that the free aldehyde group is not present. So, how do we explain this? That some of the reactions of an aldehyde group are given by glucose, whereas other reactions of an aldehyde group are not given. And the open chain structure could not also explain the phenomena of mutarotation, and it cannot also explain as to why glucose is forming two methyl glucosides. So what we have to keep in mind is that maybe there is something else which we are missing. So what we've seen, that if in a glucose molecule you have an aldehyde group and you have 5 hydroxyl groups. So what happens? That an alcoholic group can react with an aldehyde group, resulting in the formation of cyclic hemiacetal. That means what we are trying to say here is that in case of glucose, since glucose has the carbonyl group as well as the alcoholic group within the same molecule, that means intramolecular reaction can take place. Intramolecular nucleophilic addition can take place, resulting in a cyclic hemiacetal or a hemiketal. Now what was found, what we've seen and what we'll be discussing also, that in D-glucose the hemiacetal is formed by the condensation reaction between the aldehyde group on C1 and the alcoholic group on C5. So, and this results in the formation of two cyclic structures. But before I proceed further here, I had missed out one point, that you could have asked me a question, or you should ask yourself a question, that why is it that when we are treating glucose with Fehling solution, or with Benedict solution, or we are carrying out the reduction of glucose, it is giving us certain reactions. But on the other hand, it is not showing it could not explain the phenomena of mutarotation, and it also does not react with sodium bisulfite. So the the explanation that we can give here is that when we have a open chain structure, it has a tendency to occur in equilibrium with the two closed chain structures, as you can see on your screens, that when a reaction will take place between a hydroxyl group on the 5th carbon and the aldehyde group on the 1st carbon, it will react in formation of two cyclic structures. One would be alpha D glucose and the other is beta D glucose. As to how they are formed and what is the relationship between them, I will just explain. But what was found that if you dissolve alpha D glucose in water or beta D glucose in water, there is change in specific rotation. That means these three forms are now existing in equilibrium. So in aqueous solution, the two forms along with the open chain form are existing in equilibrium. So since they are existing in dynamic equilibrium, what we mean here is, now supposing we have added a reagent which reacts with the open chain form of glucose, then the mixture will behave as though it is made up of only open chain form. This can be explained on the basis that when we are carrying out the reaction, say of glucose with the Tollens reagent or with Felling's reagent or with amalgamated sodium, that is the reduction reaction, and first or the oxidation reactions, it is the open chain structure which has a free aldehyde group which reacts with the reagent, and in the process the equilibrium is disturbed. And so what happens, to maintain that dynamic equilibrium, more of the cyclic structures will be converted into the open chain structure. So the whole of the system will behave as though it is made up of only open chain structure. So that is the reason that when we carry out the reactions of glucose with certain reagents, it gives us positive test, whereas the reactions which are supposed, in this case what we find now, if you look into the structure of the alpha D glucose and beta D glucose, what we find that this alcoholic group on the 5th carbon has reacted with the aldehyde group on the 1st carbon, reacting in two cyclic structures, and in these two cyclic structures we cannot find a free aldehyde group. This is what has happened, and this is also happening here. So, and in this case, so therefore these two structures will not give the reactions with Schiff's reagent, because the open chain structure is present in very less form. Say it will be present in less than 1%, whereas beta D glucose is present as 64% and alpha D glucose is present as 36% in an aqueous solution. So now let us look into the case. So now we know that because of reaction between the aldehyde group on the 1st carbon and the hydroxyl group on the 5th carbon, we get a hemiacetal. Now you should ask yourself, what is the mechanism of this formation of hemiacetal? So the mechanism is the same, that is the mechanism which we normally follow when we are forming a hemiacetal by reaction between an individual aldehyde and an alcohol molecule, right? So, and you have to remember that I have already discussed the mechanism of hemiacetal formation of D-glucose in great details in my lecture on structural aspects of glucose, which was structural aspects of monosaccharide number 4, and I have also shared the link with you. So you can refer there. But just to recapitulate, I will again very quickly explain the mechanism. So the first thing that you should ask yourself, that glucose has 5 hydroxyl groups. Why is it that only the hydroxyl group on the 5th carbon is reacting with an aldehyde group? It is because when a hydroxyl group on the 5th carbon reacts with an aldehyde group, what you observe that you get a 6-membered ring. Here also a 6-membered ring. And this 6-membered ring are stable. We can compare this 6-membered ring to that of ring of cyclohexane. And we know that the cyclohexane rings are more stable. They are even more stable than a cyclopentane ring or a cycloheptane ring. So similarly, when a 6-membered ring is formed, that structure for glucose would be more stable as if the ring was formed between reaction of an aldehyde group with the hydroxyl group on 4th carbon or an hydroxyl group on 7th carbon, which would result in 5-membered rings or 7-membered rings respectively. So that is why the reaction takes place between the aldehyde group and the hydroxyl group on the 5th carbon. And now all this I had explained in my previous lecture as to how we will orient, we will turn the molecule at 90 degrees and proceed from there. But now what I am telling you is simple reaction, that as I have said that this is going to be a nucleophilic addition reaction, and OH on the 5th carbon will act as a nucleophile through lone pair of electrons on oxygen. And now what happens is that this carbon, the carbonyl carbon, is sp2 hybridized. So this can either attack from the top or it can attack from the bottom, since the structure here is planar. And this will result in formation of 2 diastereomers. That is, in this process, we are generating a new stereogenic center, that is carbon number 1, which was the aldehyde group here, is now being converted into this group. That is, an OH is attached to here and H is attached to here. So this carbon has become stereogenic center, that is the carbonyl carbon. Similarly, in this structure also the carbonyl carbon has turned into a stereogenic center. So when cyclization takes place, one stereogenic center increases. And now what we find that at this stereogenic center, which we can also called as epimeric center, anomeric carbon, because we know that stereoisomers which differ in configuration at one carbon are known as epimers, and because this epimer is resulting as a result from the cyclization of this molecule, we give it a special name, that is anomers. Now these two are anomers, and what is the difference between these two? That is, if we look into the structure of alpha D glucose, here alpha indicates that the orientation of the primary hydroxyl group, that is CH2OH group, and the OH group on the first carbon are trans to each other. Whereas beta indicates that this CH2OH group, that is methyl hydroxyl group, that is the primary alcoholic group, and the OH group on the anomeric carbon are cis to each other. So this would be the beta configuration, or this is the beta anomer and this is the alpha anomer. And of course you know that this D will indicate that the OH is on the right hand side at the highest numbered asymmetric carbon. Now when we are dealing with this, let me ask you one question here. This can be asked in entrance exam also, that is the anomers, that is glucose on cyclization gives stereoisomers, and these stereoisomers are enantiomers. A choice. B is they are diastereomers. C is they are epimers, and D choice is they are epimers as well as diastereomers. So what is your answer going to be? If you look into these two structures carefully, they are not enantiomers. Because what are enantiomers? Enantiomers are stereoisomers which differ in configuration at each chiral carbon. And what we find that alpha form and the beta form differ in configuration only at C1 carbon, at this carbon. In alpha form, the OH is below the plane of the ring, and in beta form, the OH is above the plane of the ring at the first carbon. And at rest of the carbons, that is second, third and fourth carbon, the configuration is same. So that means they are definitely not enantiomers. Now the question is, are they diastereomers? Yes, they are diastereomers, because diastereomers are stereoisomers which differ in configuration at one or more chiral carbons. So that means they are diastereomers. And now to be specific, they are epimers. Why are they epimers? Because epimers are stereoisomers which differ in configuration at only one chiral carbon. And in this case, they are differing in configuration at anomeric carbon, that is the first carbon. So they are also known as anomers. The next thing that can be asked from you is, which is the anomeric carbon in this structure, the alpha form and the beta form? So if you look into the structure, what you find that this carbon is the only carbon which is attached directly to oxygens. Same is the case here in alpha D glucose, that this carbon is attached to two oxygens, one oxygen and two oxygens. So whatever structure they give you, they may give you Fischer structure, which I'll be discussing, Haworth structure, or the chair form glucose. In all, you will identify the anomeric carbon by looking at the structure and finding out which is the carbon which is attached to two oxygens. So that carbon will be the anomeric carbon. So now we can see that because of cyclization, glucose will exist in three forms, that is the open chain form, alpha form and the beta form. And there will be dynamic equilibrium between the three forms. And as I've already said, because the carbonyl group of the open chain D glucose becomes asymmetric on cyclization, we will get two diastereomers which are epimers, and the specific name for these are anomers, which are alpha D glucose and beta D glucose. So this is what again I have shown here, that is cyclization is taking place here between the hydroxyl group on the fifth carbon and the carbonyl group on the first carbon, resulting in the formation of two cyclic forms. So this is the Fischer structure for it. So what you have to remember when you're looking at the Fischer structure, that in this case the OH, this carbon is the aldehydic carbon which has been converted into a stereogenic center. So in this case, OH should be on the right hand side or it should be inside the ring. If that is the case, then this is the alpha form. And if OH is written on the left hand side and it is outside the ring, that means it is the beta form. Then why are we calling it D? Because the OH on the highest numbered asymmetry carbon is on the right hand side. And these three forms are in dynamic equilibrium, in which the percentage or the concentration of alpha form is 36%, that of beta form is 64%, and the open chain structure is less than 1%. So now I want to remove the difficulties or the drawbacks of the Fischer's projection, Fischer's open chain structure, as to how were these difficulties or the anomalies removed by the cyclic form of glucose. But before I do that, I would like to discuss the cyclic structures of glucose in detail, that is the Fisher structure, Fisher projection, the Haworth projection, and the chair conformation for glucose. Thank you.